hoping others would join. Um, okay, so let me give a small recap of what you did this particular week. Oops. Yeah. So in this particular week was really interesting, right? Because you learned about something called limits and co-limits, which sort of are universal constructions that take place in a category. So in this week, the essential idea was, first of all, you learned what is the formal definition of a diagram in a category. I mean, certainly we have been talking or speaking about diagrams. In fact, we have been speaking about commutative diagrams in a category. But the intuitive idea was that behind a diagram was that it consists of objects and arrows, right? So the formal definition is it's a functor from a category I into some category A, and limits. So the idea is to find out the limit or the co-limit of this diagram D, and for that we usually require I to be a small category. So I is actually called the shape category, and it's assumed to be a small category. Depending on whatever shape I has, the corresponding diagram D in the codomain category A looks exactly the same, is of the same shape. So D is called a diagram in A of shape I. That's all, right? Or of type I. Okay, so having studied what a diagram is, you understood the concept of finding the limit of the co-limit of the diagram D. Right? So in analysis, by the way, are you a math student?
No, I'm a computer science student, and
Okay, but I'm pretty sure you have studied BIGO notation and all those things, right?
I've
Complexity.
studied. I know about the connotation.
Yeah, so you know about analysis and you know what sequences and limits of sequences are, right?
Like analysis of algorithms. Certainly, I haven't like studied that in college, but I've seen a YouTube video where they like do the analysis of an algorithm, like by analyzing the loops used.
Okay, so by
Something like that.
analysis, I actually mean real analysis, which is a subject of mathematics, a discipline of mathematics. But, anyways, you have done limits in 10 plus 2, right?
Yes,
Yeah.
yes, yes.
So, in real analysis, what you do is you find limits of sequences, right? So, what you essentially do is you take a sequence of real numbers, is exactly which exactly looks like this. So x1 is a real number, x2, x3, and so on, and you find the limit of this sequence. Okay, so a sequence can also be thought of as a function f from natural numbers into r. Okay, so this is how you think of a sequence, and what you find out is the limit of this function, the limit of this sequence, right? In category theory, the function gets replaced by, so function, this gets replaced by a functor D, which we are calling our diagram. And what we want to do is find the limit of this diagram. And as it turns out, since category theory has more structure, you can talk about dual or the opposite category of a category. So besides limit, you can also talk about co-limits. Okay, so a function in analysis, a sequence in analysis gets replaced by a functor in category theory.
What gets replaced by a functor?
A map, a function.
Oh, okay.
And what you want to do is you want to find the limit or the co-limit of this functor.
So the objective is to find the limit or the co-limit.
Yes, that is what you that is what the lectures covered this week, right?
Um, I guess.
Okay, I see. Yeah, please do have a look at the videos. I mean, Sir Amit sir is a better, far better teacher than me. So please do have a look at the videos. And yeah, so what I was saying is, you find the limit or the co-limit of this functor. That is the objective, right?
Sir, one more thing.
Yeah.
In the actual NPTEL exam, like, will we have MCQs or do we have to like write descriptive answers?
I really am not the right person to answer this. You can contact either Amit sir or you can text in the discussion forum.
This discussion forum is on the NPTEL website.
Yeah.
Okay, sir.
Yeah. So that is what you. So you in this particular week, what you wanted to do is find the limit of the co-limit of a diagram. That is a functor. That's all. And you saw different kinds of limits and co-limits. So limits or co-limits are like umbrella terms. They themselves are universal constructions, but they are like umbrella terms for a large number of standard limits that you study. So you studied examples of limits and co-limits. So for example, terminal objects are limits. Dually initial objects are co-limits. Then products are limits. Co-products are co-limits. Equalizers are limits. Co-equalizers dually are co-limits. And for each of these specific limits, the diagram whose limit you are taking has a particular shape. So for terminal object, the diagram or the shape category, I should say, that is a category, small category I, for terminal objects is empty. So let's write this table nicely. Oops. So for if the shape category is empty, then the limit of the corresponding diagram, there is a unique functor from empty to any category, empty category to any category. So the limit of this functor from empty category to any category is a terminal object. The co-limit is an initial object. If the shape category is a discrete category in the sense that the only arrows are identities, then the corresponding limit is product and co-limit is co-product. If the shape category looks like this, then the corresponding limit is an equalizer. The corresponding co-limit is a co-equalizer. If the shape category looks like this, okay, looks like this, then the corresponding limit is a pullback. And for co-limits, we don't, you of course have a co-limit of such a diagram, but it's easy to understand if you have seen the definition of a co-limit. It's easy to understand what that co-limit will be. So it's not very relevant in the co-limit case, this kind of shape. On the other hand, if you look at the opposite shape, the opposite category of this, which looks like this, the limit is easy to understand. It will exactly be the value of the functor, the diagram at this object. and the corresponding co-limit will be a push out, and so on. There are many other examples, but these are the relevant kind of limits and co-limits which this course will be interested in, and these were introduced in this particular week. Okay.
Sir, a bit of a simple question, but
Yeah.
what are those three different types of arrows called? Do they have a name or something?
What do you mean? You mean special arrows in a category?
Yeah, in the shape category that you have drawn, like.
Oh, in
What do
this
we refer to
particular
them as?
category. I mean,
Huh?
are you talking about this category?
Yes.
Yeah, I mean they are arbitrary arrows. This is just a shape category. You can think of this as some object, some object, some object. There is one arrow from this object to this object. There is one arrow from this object to this object.
Okay, and since there is a dash for co-limit, that means co-limit doesn't exist.
No. Co-limit exists. I mean, see, this of course depends on the category, the second category, the codomain category in which you are taking the co-limit. But and co-limit of a diagram in a category might not exist. There are many examples of categories which don't have this property, and in fact, categories in which co-limits exist, all co-limits exist, have a special name, which are called co-complete categories. But the point is that for any diagram of this shape, the co-limit will always exist, and it will be the value of the diagram that is the functor at this object. Since it's very trivial, and I mean it's not very useful here, because the co-limit, usually if you take a diagram in a category, if it looks like this, let's say, then the co-limit is an object in the category together with arrows, right? That is what was taught this week. That is, this is a cocone on this diagram, which is universal among all cocoons on the diagram. So this co-limit thing is some object in the second category, which in most cases, I mean in most cases, that object is not an object from the diagram itself. Okay, it's some other object. It's some object which best approximates the diagram. That is the idea of a co-limit or of a limit. But here it turns out that the co-limit of any diagram of this the co-limit of any diagram of this shape will exactly be the value of the functor, the diagram at this object. So the co-limit is an object in the diagram. I mean, that can happen, of course, but that is why it's not very interesting. Okay, so co-limit will exist in this case, but it's not interesting. That's all. By the way, this kind of a shape, or this kind of a any diagram of this shape is called a cospan. That's just a name. Okay, so any diagram of this shape is called a cospan, and any diagram of this shape is, of course, will be called a span. So the idea is that limits and co-limits are actually dual notions of each other, and I mean, we won't be discussing the definition again, but the idea is, if you take a functor d from I into a diagram in A of shape I, that is, then the limit of this diagram, and I'll say that, if you take this diagram, you can also consider the opposite functor d op from I op to A op. There is, of course, an obvious functor from I op to A op, because using d you can define it. We have seen it previously, right? You just send an object I to d of I only, and you send an arrow I to j, let's say f op in I op, which is exactly an arrow f from j to I in I to d of j. You should have an arrow in A of from di to dj, so you just take d of f op, d of f op, yeah. So d of f will be an arrow from dj to di in A. So in the opposite category, it will be df op will be an arrow from di to dj. That is what your functor is, right? So the idea is that the limit of the functor d is exactly the co-limit of this functor. The objects are the same and the arrows are just reversed. Is exactly the co-limit of the functor d op. In that sense, these two notions are dual notions of each other. Okay. I mean, of course, we are saying a lot here. It needs to be. I mean, you can go back and check this. The idea is always this, that for limits, for any diagram whose limit you want to find, you just look at cones on the diagram, and the limit of the diagram will be the cone which is universal among all cones on the diagram. For co-limits, you just reverse the arrows. So now you have a diagram. For the co-limit of the diagram, you should look at co-cones on the diagram. That is, cones under the diagram. Sometimes also people say it like this. And you look at the universal co-cone that is on the diagram. That is the universal cone under the diagram. That is what the co-limit is. So these are formally dual notions.
D is a functor, right?
D is a functor, yeah. D is a functor. D op is also a functor.
Okay, D op is also functor. And we take a limit on D. We use the left arrow.
Yes, to denote limits, and the right arrow to denote co-limits. Alternately, you can just write it like this. I mean, you can just say limit of D, and you can write it like co-limit of D. That also you can write. The point is that you want to find the limit of a diagram D, that is a functor D. You want to find the co-limit of a diagram D, that is a functor D. Okay. Right. So let's start whatever we want to do this week based on the material covered so far. Yeah, I forgot to introduce myself. I have to do this. Sorry. So I am Shubhajit. I'm a PhD student at IISc, and welcome to week 4. Yeah. So suppose C is a category. Show that pullback squares in C satisfy the following gluing property. That whenever you have a commutative diagram like this, which means that this commutes as well as this commutes, and hence the overall perimeter commutes. If the right hand square is given to be a pullback square, if this square is a pullback square, this information is given to you, then you have to show that the perimeter square, that is a big square, will be a pullback if and only if the smaller square is a pullback. That is what you want to do, and formulate the dual result, which of course it's understood what it will be, but we'll come to this. Let us try this first. Before that, just to be comfortable, we won't be getting into the definition of what the limit of a functor is, but that is the limit. We won't be discussing the precise definition of the limit of a diagram, but let's quickly recap what pullbacks are. So you take a diagram in a category like this, which is exactly a diagram that is a functor from this category to your category C. So you take a diagram like this. What is the pullback of the diagram? If it exists at all, what is the pullback of this diagram? I just want to know if you have seen the lectures this week or are aware of this, because otherwise we will have a problem in proceeding. Anyone? What is a pullback? By the way, I have a question. How many of you have registered for the course? Did both of you register for, for the exam?
Yes, sir. I registered for the exam.
Okay. And Shruten, did you register?
Yes, I also have registered.
Okay. So tell me, what is the pullback of this diagram? That is this functor. So again, if you check the definition of the limit of a functor, you can apply that definition here. As I said, this is just a functor from this category into our category C, which maps this object to A, this object to B, this object to C, this arrow to this arrow, this arrow to this arrow. So if you find the limit of this functor, you can understand that you can find out the exact definition of pullback. Pullback is a limit. But let's just recap what the definition of pullback is. Does anyone remember? Okay, we'll just mention this once, that the pullback of this diagram, which is a cospan, is an object together with arrows from P to A, P to C, such that this square will commute. And not only so, this triplet that you have of this object together with these two arrows, this is the universal one among all such triplets with this property, which means that if you take an arbitrary object x together with an arrow x to A and an arrow x to C, such that this big diagram commutes, then this new triplet, this arbitrary triplet, will factor uniquely through this one, the universal one. So what do I mean by this? What I mean by this is there will exist a unique arrow from X to P which makes both small triangles commute. So essentially this thing, this arbitrary thing, is factoring through this universal thing. Okay, because so this arrow can be written as a composition of this with this, and this arrow can be written as a composition of this with this. Okay. And this factorization needs to be unique. There should be a unique arrow from X to P, making both triangles commute. That is what pullback is. So for example, pullbacks might not always exist in a category. In the category of sets, it does exist. So in the category of sets, if you take a diagram like this, so A is a set, B is a set, F is a function. So this is in the category set. C is another set, this is a function G. Then the pullback will exist, and the pullback, which is usually written like this in an abstract category, is exactly this set of pairs A comma C, where A is in A, C is in C, such that f of A is equal to G of C. That is what the pullback is. And this maps at the obvious projections. Okay, and this will, you can check, is a pullback square, in the sense that this triplet will actually be the universal one, making this square commute. Okay, so now we know the definition of a pullback. So let's try to solve the problem. We need to show that pullback squares satisfy this pasting property, or the pasting law, which says, which I'll reiterate again, says that if you have a commutative diagram like this, such that the right square, this one, is given to be a pullback, then the entire perimeter, by which I mean this square, so this object together with the perimeter square is this, so this object together with this arrow, composed arrow, this arrow, this arrow, and this arrow, composed arrow, will be a pullback if and only if this left square is a pullback. That is what you want to show. So let's try to show the easier version, or the easier one, easier side, which is, we assume both squares, both smaller squares are given to be pullback squares. We need to show that the entire square, the large square, the perimeter square, is a pullback square. So we'll mostly use pictures here, so we won't name the objects. So assume first that the left square is a pullback indeed. So what you have is this is your left square given. This is assumed to be a pullback square, and the right square was already given to be a pullback square. We want to show that this perimeter, this large square, the boundary square, is also a pullback square. So let's just name the arrows. This is F, let's say this is G, this is H, this is K, L, M, N, let's say. Okay. We want to show that, yeah, I'll write the names here. In fact, F, G, H, K, L, M, N. Sorry, yeah. So to show that the large square is a pullback square, that is to show that this square, so this is LF, the composite, this is M, this is H, this is NG. We want to show this is a pullback square. First we need to guarantee that this object together with this two arrows makes this square commutative, which is already given to us. This is a pullback square, it commutes. This is a pullback square, it commutes. So this large square will be commutative as well. Okay. Now let us show that this is the universal triplet making this square commute. So assume that you have some arbitrary object. Let's say this. We are not naming the object, just treating it as a dot. Together with two arrows, let's say A, and you have another arrow B, such that, so assume that there are arrows A, comma B, which we have, we are not mentioning the source object and the target object here. We are just treating them as dots. So assuming there are arrows A and B, it is clear from the picture what they are, such that MA is equal to NGB. That is, this square is commutative. This particular square is, I mean, formed by these arrows. It's understood what I am saying. Yeah, this square is commutative. So we want to show that we want to show that this triplet factors uniquely through this one, through the given one. This is what we want to show, right? So what we want to show is there should exist a unique arrow from this to this, which makes both triangles commute, right? So question is, how do you get this unique arrow? So how do you find out this unique arrow, or how do you show that there indeed exists a unique arrow making both triangles commute? So we haven't really used the information that this is a pullback square. We have assumed that this is a pullback square, and we haven't used the information that the right hand square is also a pullback square. We need to use all this, right? So how do you show this? How do you show this? Yeah, what do you think? In fact, let us just use that original diagram here. I mean, the data is the same. We are just keeping the squares. We are not composing them or gluing them as such. So this is our object. This is an arrow from this object to this object. Let's say this is B. This is an arrow from this object to this object. From this to this. Let's say this is A. Yeah. Okay. This should be B and this should be A. This is A. Yeah. MA is equal to NGB. How do you show this now? What do you think? Keep in mind the left hand square is a pullback, the right hand square is also a pullback. We need to use this.
Because the right square is a pullback. You have a unique arrow from our object to the top middle object,
Yes, very good.
and
And
then so now you have arrows, and then you have again, because the left square is a pullback, you have a unique arrow from that object to the top left.
okay, okay,
So
okay,
then, because the arrow is unique, now the outer square is also a pullback.
okay. So I mean, exactly correct. So let's go step by step. So what is step one? Since the right hand square, since the right square is a pullback, so what do you need to make? I mean, to use a universal property of the pullback, you need to make sure that this arrow, when composed with this arrow, should give you this arrow composed with this, composed with this. I mean, from this object to this object, you are taking the arrow A. From this object to this object, you should have an arrow, and that arrow is this composite GB. Okay. So what you need to make sure is this M composed with A should be N composed with G composed B, but that is already given to you, right? So since the right hand square is a pullback and MA is equal to N composed with, I'll write it like this, G composed B, to make sure that you are taking this composite arrow from this to this. Since this holds, there exists a unique arrow. So we'll just draw it. Let's use a different color for this. Maybe a darker color. From this to this, which we'll call, let's say, what letter is left? C. There is a unique arrow C, such that, as indicated in the picture with the given source and that target, such that, so this is unique, such that L composed with C is equal to A, and what else do you have? K composed with C is equal to GB or G composed B. This to hold. Now what is step 2? Actually what you want is an arrow from this to this, right? So what is step 2? So now observe that the left hand square is a pullback square. You have an arrow from this object to this vertex, and you have an arrow from this object to this vertex as well. What you need to make sure is these two arrows, you need to make sure that this arrow composed with this arrow should be equal to this arrow composed with this arrow. Then again you can apply the universal property of this pullback square, right? So how do you do this? So need to make sure. So step 2, observe that, okay, step 2, observe that K composed with C, which we don't know what this is yet, is equal to G composed with B, and that is already given to us because this is what we want, right? This composed with this should be equal to this composed with this, but we already know that C already has this property that K composed with C is G composed with B, and hence by the universal property of the pullback square, of the left pullback square, excuse my handwriting, of the left pullback square, there exists a unique arrow from what to what? From this object to this object. Let's call this arrow to be, let's use a different color. I don't know, let's say blue. Let's call this arrow D. There exists a unique D. So there exists a unique arrow D such that this triangle should commute. This arrow composed with this arrow should be this, and this arrow composed with this arrow should be this. So such that what are the names? K composed with F composed with D is C. F composed with D is C, and uh, H composed with D is B. Right? This is what is given to you. So we claim that this unique arrow will actually be the arrow that we wanted, right? That is what we want. So what we need to show is this arrow composed with this arrow composed with this arrow should be this arrow, and this arrow composed with this arrow composed with and this arrow composed with this arrow should be equal to this arrow. That is what we want. That is what we wanted, right? So we need to show that LF composed with D should be equal to A, but observe that that is already given, because LF, so now LFD is equal to LC, because FD is C, and what is LC? LC is A. So this triangle commutes, right? What else? You need to show HD is B, but that is already given to you, and HD is already given to be B. This is what we had, right? So this arrow D certainly makes both triangles commute. This commutes and this triangle commutes, right? What we need to show now is this is the unique such arrow that makes this commute. So if L prime is an, what is the arrow that we took? D. So let's take D prime. If D prime is an arrow from this object to this object, if you take another arrow D prime making this big triangle commute and this commute, we claim that D should be equal to D prime. So let's draw this arrow like this. Let's say this is D prime. Okay. Let's say this is D prime. Yeah. Suppose So this is green in color. Green, and D is blue. Just so that people don't get confused. If D prime is an arrow such that LFD prime is equal to A and HD prime is equal to B, we need to show that D prime should be equal to D. And why is that the case? Why is that the case? Assume LFD prime is equal to A and HD prime is equal to B. How do you have that D prime should be equal to D? Keep in mind that the arrow D was obtained using the universal property of the left pullback square, right? D was the unique arrow making this two equations correct, or making this two triangles commute, this triangle and this smaller triangle. So if D prime, so it's enough to show that the arrow D prime also makes this to commute, and then D will be equal to D prime. Now already this commutes because we assume that H composed with D prime is B. This is already correct. We just need to show that this triangle commutes, and then the universal property of the pullback will guarantee that D must be equal to, of the left pullback square, that is the smaller pullback square, will guarantee that D should be equal to D prime, right? So what you need to show is that f D prime should be equal to C. So we claim that f D prime is equal to C. Why is that the case? We need to show f composed with D prime, this arrow composed with D prime is equal to C. How do you show this? Keep in mind C. How was C obtained? Again, C was obtained using the universal property of this square, right? So C was that unique arrow which makes these two triangles commute. This triangle commutes, and this composed with this should be equal to this. Yeah. So C was a unique arrow such that K composed with C is GF and L composed with C is A. Right? So to show that if D prime is equal to C, we can just show that if composed with D prime also makes this to commute. Okay, so uh, so this arrow composed with this arrow composed with this arrow should give you the arrow A, and this arrow composed with this arrow composed with this arrow should give you this arrow. That is what we need to show. Okay, so how to show this? I mean, this will be a triviality. uh, let's just quickly get to the details. So f d prime, right? Yeah, so lf d prime should be equal to A. That is what we need to show. So enough to show that f d prime lf d prime is equal to A, which is already given to us because we assume d prime is an arrow making I mean such that lf d prime equal to A and h d prime equal to B. So one of them is already given to us. So given by assumption, and we also need to show this, right? That this arrow composed with this arrow composed with this arrow, I mean f d prime composed with K should be equal to B composed with G. So GB is KF D prime. This is what we also need to show. So what did we have? KF D prime is GB. That is what we want to show. So KF D prime is equal to GB. Now how do you obtain this? Just go through the given written stuff. I'm pretty sure we have this. KF D prime is equal to GB. It is already given to us that H D prime is B, right? H D prime is B, and what do we know about KF? Yeah, KF. Oops. Since we know that KF, this square is commutative, so K composed with F is G composed with H, right? So since the left square commutes, KF is equal to GH, and now we are done. So KF D prime is equal to GH D prime. H D prime is B, so this is just GB, and that is what we wanted to show, right? So we observe that both C and F D prime make those two triangles commute, which implies that C must be equal to F D prime because C was a unique arrow with this property. So C must be equal to F D prime. So C is equal to F D prime by uniqueness. I'll just write it like this. Now since C is equal to F D prime, we are done, right? That is what we wanted to show, because if C is equal to F D prime, so C makes this to commute. I mean D makes this to commute. So D composed with F is C, and this is already known to us. This commutes, right? So I mean sorry, D prime composed with F is C. That is what we showed, and we already know that by assumption this is commutative. So both these two small triangles commute, which means D is equal to D prime. So D is equal to D prime, again by uniqueness. Okay, so we won't be spending time in the other part of this. The other part is, I would say, more interesting. Please try this. The point of the exercise was to not, I mean, it's okay if you didn't follow through the entire proof, but the spirit of the proof I hope is clear to you. I mean, this is how exactly proofs in category theory work, right? So this is how you argue with arrows. That is why category theory is sometimes called arrow theory. Okay, because you work with arrows. That's all you do. You can give proofs using pictures. You don't need to write stuff. Okay, so what we wrote here is essentially algebra, and commutative diagrams are analogs of algebra in category theory. So what you are in what we could instead do, instead of writing all this, is just look at the picture and draw stuff, draw arrows. Okay, this is the spirit of proofs in category theory. Okay, so this is okay, and I'll just write a note that check that this other thing also commutes. Check that the converse is also true. By which I mean that the if the entire perimeter is commutative, is a pullback square, then the left square is also a pullback square. So please do get back and check this, that the converse is also true.
Excuse me, sir.
Yeah.
Sir, my audio got cut a little. Can you repeat what you said from? So D is equal to D prime by uniqueness, and this is the spirit of the proofs in category theory. That was the last thing I heard.
Okay, so we did you I hope you understood the proof. I mean, at least the spirit of the proof.
Yes. So we basically show that using the properties of pasting law and pullback co-limits, that
No,
whatever
pullback
is
limits.
required
Pullbacks are limits. They are not co-limits.
Yeah. Using the properties of pullbacks, we showed whatever is required.
Yeah,
basically.
exactly. That is what we showed. And what I'm asking, what I said during the time you are not here or couldn't hear, was to verify that the converse is also true, in the sense that if the entire perimeter is a pullback, try to show that the left square is a pullback. Okay. If you get stuck, do email me. I always mention my email ID, or mention in the discussion forum. Someone will be there to answer this. Okay, let's get to the next problem. We will only be solving 4 problems today, because that is how I mean, otherwise it's not, we always go over time. So we'll just solve 4 problems today. So let's get to problem 2, which says that suppose G is a group considered as a single object groupoid. So we have seen this, that a monoid is exactly a category with a single object. A group, which is a special kind of monoid in the sense that all elements of the monoid are invertible, should correspond therefore to a category with a single object which has some special property. Namely, all arrows in that category should be invertible, that is isomorphisms. So that means that the category should be a single object groupoid. Right. So a group G can be considered as a single object groupoid. And now what you do is, considering G as a single object groupoid, that is as a single object category in which all arrows are isomorphisms, in particular G can be thought of as a single object category. So you take a functor from G to the category of sets. What the question is asking for is to find the co-limit of this functor. Keep in mind that G here is our shape category, right? And what this functor is exactly a diagram in set of shape G. So G looks like this. This is your G. This is the category, this G. This is the shape category G. There is only one object, and the arrows in this category are exactly elements of your group. So G, G prime, G double prime, G triple prime, and so on. This is what your shape category looks like. You are taking a functor F from this category into the category set, which is, as I said, is just a diagram in set of this shape. So it should look something or exactly like what? So what does a functor do? It should map the, a functor consists of, firstly, a mapping of the class of objects of the first category into the class of objects into the second category, right? So there is only one object in the first category. So the functor just needs to map this single object, because this is the only object here. So this gets mapped to some object f of dot. Let's call it some set A. Okay. And it maps arrows to arrows in the second category in the sense, in such a way that domain and codomain operations are preserved, which is of course preserved in this case because there is only one object. So any arrow G will get mapped onto, so if you take an arrow G, it will get mapped onto some arrow fg from A to A, right? And since f is a functor, it should preserve all the structure, right? So in particular, f should commute with compositions as well and identities, by which I mean that f should preserve compositions and f should preserve identities, right? So f of g prime dot g, so g prime composed g is just g prime dot g in the group, which is equal to, should be equal to f of g prime composed with f of g. Okay, so note that f of g is an arrow in the category set, by which I mean therefore that f of g is exactly mapping from the set A to itself, right? An endo arrow, an endo mapping in this case of sets in this case. Yeah, so my question, so giving a functor from G to set is exactly giving an object A of set together with, for every element little g in capital G considered as an arrow in capital G, you should have an arrow that is a function f of g from A to A in such a way that these two laws hold. F of g prime dot g should be f of g prime composed with g, f of g for all g prime in G, and f of 1 on dot, the identity arrow on dot, which is exactly the identity element of your G. We have seen this many times. That is how the category G is defined. So f of E, the identity element of G, should be equal to 1 of f of dot, that is 1 of fa, that is the identity mapping on the set, 1 of A. F of dot is A, so 1 of A, which is the identity mapping on the set A, right? So my question is, what exactly is this f? What exactly is a functor therefore? I'm not expecting an answer from Srisha. Shruten, are you from a math background?
Yes.
Okay, so what are you studying currently? I mean, which what?
I'm in third year BTech right now.
So how? Okay, so you did your mathematics before doing a BTech.
No, I mean I'm doing maths and computing.
Oh, I see. Where are you studying?
MIT Manipal.
Oh, I see. Okay. So probably you'll be able to answer this. I'm sure. I hope so. What exactly is f? What exactly is the data of a functor f now? So keep in mind if, so let's write down the usual way of writing a functor f. So first of all, as I said, it should, a functor f, so f consists of firstly a mapping from the class of objects of G, so obg, which here is a singleton, consists of exactly one object, to the class of objects of the category set, right? That is all sets, right? Here obg is exactly equal to a singleton, right? So a mapping from this to ob set should exactly give you a set A, right? Secondly, it consists of, for every pair of objects in the first category, here there is only one object in the first category, so for the pair dot comma dot of objects in the first category, this is the only pair involved, right? So for every pair you should have a mapping from what to what, from the hom set G of dot comma dot, right? So for every pair A comma B, you have a mapping from, I mean, if the functor is from A to B, by definition, for every pair A comma A prime of objects in A, you have a mapping from this to B Fa comma Fa prime, right? Fa prime. A mapping at the level of hom sets, local mapping. And before that, you have a mapping from the class of objects of A into the class of objects of B, right? Sending A to Fa. And this sends an arrow F to Ff, right? So the first mapping sends any object A to Fa, and the second mapping sends any arrow F from A to A prime onto some arrow Ff from Fa to Fa prime. So we are just specializing the definition of a functor in this specific case. So there is exactly one pair which of objects dot dot in the first category. So for dot dot, you should have a mapping from G dot dot into set F of dot comma F of dot, which is just set A comma A. That is the set of all endomorphisms of the set A. Endo mappings, endo arrows. And what is G of dot dot? G of dot dot by definition, the hom set from dot to dot in the category G is exactly the underlying set of G, right? Every arrow is exactly an element of G. So this is just the group G. So you have a mapping from G to set AA, which we can write as end A, such that, let's have a notation. So if an element G gets mapped to F of G, which is a set map from A to A, that is an endomorphism of the object A. So F of G, let's call it sigma G, such that F should respect composition. So F of G prime dot G should be Fg prime compose Fg, by which I mean therefore that, so by our notation, such that sigma G prime G, which is F of G prime dot G or G prime composed with G, should be equal to F of G prime composed with F of G, which is exactly sigma G composed with sigma G prime composed with sigma G. And what else do you have? Sorry. What else do you have? You have and sigma at identity, which is F of 1 on dot. I'm messing it up. What else do you have? F of E is, yeah. So what you have is sigma E, which is F of E should be equal to, yeah, F of 1 on dot, should be equal to 1A, the identity map on A. So we have basically rephrased the definition of a functor F from G to set in this way. It consists of a mapping from G to the set of endomorphisms of A, of some set A, such that these two laws hold. What are these two laws exactly saying you? If you call this mapping F, sending G to sigma G, what are these two laws actually saying you? Just look at the notation. What are these two saying? I mean, we didn't even write to this, get to this notation. We can just forget this notation and just keep in mind what if was. This is just confusing. What we have is these two laws hold. So if, so this, let's call, so this is F, such that F G prime G is equal to F G prime composed F of G, composed with F of G, and F of G prime, F of identity is 1 on A. What is this saying you exactly? What is this saying you exactly? What is F? G is a group. The right hand side is not a group, but it's a monoid, right? Endomorphisms of an object. What is this saying you exactly? Precisely the
F is a mapping, sort of, right?
F is a mapping that we know, that we always know. It's a mapping at the level of Hom sets. But does this mapping have have a special property as indicated by these two laws? Okay, let's make this even more clear. This is a monoid, but we claim that the mapping F in fact factors through what should I say? It factors through a group contained inside end of A. So why exactly is this the case? Note that F is a functor, and I'm pretty sure you remember from your previous from the previous lectures that functors always preserve isomorphisms, right? So if something is an isomorphism in the domain category, then the image arrow should also be an isomorphism in the codomain category. Here, G is a groupoid. Every arrow, that is every element of G, is invertible, is an isomorphism, right? So f of G should also be invertible, should be an isomorphism. So f of G is a map from A to A. So it is not just an endomorphism from A to A, it's an isomorphism from A to A. That is, it is an automorphism of the set A. In other words, it's just a permutation of the set A, right? So note that our map F, G to end A, factors through the inclusion of I mean, you have seen this in group theory, right? Permutations of a set are written by essay. That is what Herstein used to write, but there are other notations, I think. Anyways, through the inclusion essay into end A. Essay is set of or group of permutations. This is the group of permutations of A. So what I mean by this, you have a factorization like this: G to end A. This set map F factors through this inclusion. So you should have an arrow, some arrow from G to SA. Let's call this. Let's use the same letter F. So what you have is a map F from G to SA, and this mapping satisfies these two properties, that f g prime g is f g prime compose f g, f e is 1a. Question is, what is this mapping F? What does F satisfy? F of g prime g is f g prime composed with f of g, and f of identity is 1a. What is this mapping F? G is a group, SA is a group, and this mapping F satisfies these two properties. What is this mapping F? What kind of map is F? F is a?
It's a group homomorphism.
It's a group homomorphism. So F is a group homomorphism. So what is a group homomorphism from a group G to the group of automorphisms or permutations of a set A? What is that called?
It's an action of the group one.
Exactly. So the data F from G to set, this functor, is exactly an action. Conversely, if you have an action, you get a functor like this of G on some set. Okay. Srisha, if you haven't seen what actions are, please go back and have a look. I mean, pretty simple. The idea is very simple. So it's basically, if you have a group G and if you have a set A, the group G acts on A in the sense that if you take any element G in G and any point A in A, then G, sort of think of G as a carom striker and this point A as a
Pawn.
yeah, whatever, yeah, and G sort of pushes it to some element B. in A.
Okay, so a transformation within the set.
Yes, so every element of the group gives you a transformation sigma g from A to A, which is a permutation, a bijection from A to A.
Okay, we call it a permutation here. Okay.
Yeah, because a bijection from a set to itself is exactly a permutation of the set, isn't it?
Oh yeah.
And
So you're saying
this,
set has been altered, so we call it that.
yeah, and sigma and this sigma g's together satisfy some laws of their own. I mean composition and which are exactly this ones, the ones prescribed by these two lines.
Wait, when the set changes, the laws also change, right? That's what you're saying?
Now the set is fixed here.
Okay.
A is a fixed set, right? A functor from G to set gives you a fixed set A, namely the image
Mm-hmm.
of the unique object in the domain.
Mm.
Yeah, so the set A is fixed. This is just an action of G on A. So every element of G gives you a bijection from A to A, and this bijections should satisfy these two laws, that sigma of E should be the identity bijection and sigma of G prime G should be equal to sigma G prime compose sigma G. This is the data of an action.
Okay, so even after the permutation, those laws have to hold true for it to be valid.
No, there is nothing called even after the permutation. That doesn't make any sense. Sigma G is just a bijection from A to A. Think of it like a map. Okay. If this permutation thing is sort of confusing you, think of it like a bijection.
Okay.
Okay. Any bijection from a set to itself can be thought of as a permutation of the set. But if it's confusing you, there's nothing called after, before in mathematics, right? There's nothing to capture time in mathematics. That doesn't make sense. The idea is sigma of E should be identity and sigma of G prime G is equal to sigma of G prime compose G. This bijection should be compatible with each other in this sense. Okay. Right. So we didn't get to the main part of the problem. The main part of the problem is to find the co-limit of the functor f. Yeah. So again I am asking Shrutin, what do you think the co-limit should be? I mean, since the question has been asked, it should be some special object. I mean, the co-limit should be, and by definition the co-limit of a functor into set should be an object of set. Some object of set. Right? Because it's a diagram in set which exactly looks like this, right? The diagram exactly looks like this. So you have a set A together with sigma G prime, sigma G double prime. All these are permutations, bijections. So this is exactly how the diagram looks. There is exactly one object, but that doesn't matter. The point is that this is a diagram in set. Right, in the category set. So the co-limit of this diagram should also be an object in set by definition, right? Because if you take any diagram in a category A, suppose you are taking this diagram of objects and arrows in a category A, right, which is exactly a functor from I into your, I mean this big thing is your category A. A functor from I into this is exactly a diagram. The co-limit of this diagram is by definition an object of A. So the co-limit of our functor that we have here, even though, I mean, doesn't matter. The co-limit of our functor that we have here should be a set, right? The co-limit of this diagram should be a set. So my question is, what set do you think this should be?
Maybe because we're talking about group actions, maybe the set of orbits.
Correct. Absolutely correct guess. Absolutely right guess. Okay, so yeah, tell me, did the lectures talk about cocoons on a diagram or cones under a diagram? Was this language used? I'm sure it might have been used, right?
I think it was, but I don't remember exactly.
Okay, fine. So we need to find the co-limit of this diagram. So the co-limit of the diagram is the universal cocone on the diagram. That is a universal cone under the diagram. So first of all, what does a cone under this diagram look like, or what does a cocone on this diagram exactly look like? A cocone, So this is our diagram F. A cocone on the functor F is an object X in set together with an arrow from every object in the diagram to X, right? Now the diagram only has one object, so we just want one arrow from A to X. That's all that we want, together with an arrow A to X, that is a function in this case in the category set, such that all small triangles should commute. Whatever is here should commute, right? So take X, A to X, you have a function let's say F, right, such that all things should commute. So I mean a cocone is just a natural transformation from the functor F to the constant functor on X. That is what a cocone on the functor F is, right? So this is how it is usually defined. A cocone on a functor F is exactly a natural transformation from F to the constant, to a constant functor. So it's a natural transformation using the naturality. It should satisfy the naturality axiom. So you can just see that the naturality axiom translates to this, that this for any element G in the group, which is an arrow in the domain category, you should have a commutative diagram like this. So sigma G, this is F, this is F. This should commute. So together with a function A to X, such that F composed with sigma G should be equal to F. We have used the notation sigma G, right? Which is a bijection of from A to A. This should hold. This is exactly the data of a cocone on the functor F. Right? Now tell me, what is the colimit of this functor? It should be the universal cocone on this functor. So what exactly should the universal cocone be? So the colimit of the functor F is the universal cocone on the functor. On the functor. That is the initial cocone on the functor F. That is, it is a cocone. So a cocone we just saw consists of exactly one set. Let's say C is your set, together with a function A to C, let's say U, such that for any arbitrary cocone on the functor, so arbitrary cocone is, let's say A comma, X comma A to X F. This is the, so the cocone part is this, right? This data is the cocone part. This data is the cocone part. A is already given to you. This data is the cocone part, right? So together with a function A to X, right? So for any arbitrary cocone on, so a cocone is exactly a set together with a arbitrary function A to X. For any cocone on the functor F, what is the universal property of the colimit? It is a universal cocone. It is an initial cocone, which means that there should exist a unique arrow in the category of sets. So a function from what to what? From the universal one to X. Let's say this is F prime, such that all small triangles should commute. Here we only have one triangle. So what is your triangle? So you have, So this is A, the object A, which is the part of the diagram. A to X you have F, A to C you have U. You should have a unique arrow. C to X, which is F prime, such that this commutes. So that is F prime U should be equal to F, right? So question is, what is this? What is this C comma U, right? And as Shruten has already guessed, it should be the set of orbits of the action of G on A. Okay, it's a bit difficult to describe what orbits of an action are right now, because it will take some time. How should I say this? Okay, well, I'll try to summarize the idea. So the idea is pretty simple. I mean, if G is a group acts on a set A, call this set, so for each A, for each little a in A, element little a of the set, you call this set OA, which is defined in this way: G dot A, I mean sigma G applied on A, which is G dot A, in our notation of an action, such that G is in capital G to be the orbit of A. So what is it exactly? It is exactly the trajectory of the point A in the set under the action of the group. So wherever A goes, you collect all those elements together. So A is hit by all elements of the group G. It goes to different points. You collect all those points together. In particular, A goes to A because identity element should fix it, right? That is one of the axioms actually says. So this is called the orbit of A, and it turns out that the orbits are actually equivalence classes for some equivalence relation on the set. What is that equivalence relation? That an element A is related to an element A prime if there is some group element G taking A to A prime, that is such that sigma G of A is A prime, or such that G dot A is A prime. That you can check is an equivalence relation on the set, and the equivalence classes are exactly orbits. So the set of all equivalence classes is the set of orbits. So if that equivalence relation is tilde, so tilde is defined in this way: A comma A. So so define binary relation tilde on your set A as follows. So G, keep in mind G and A are fixed, and there is a fixed action of G on A, right? So define a binary relation tilde on A as follows, that an element A is related to A prime if and only if there exists some group element G in G such that sigma G, this bijection from A to A, sigma G is a bijective map from A to A. Sigma G in particular should take the element little a to A prime. Sigma G of A by our notation is just G dot A. Okay, this is your relation. Check that tilde is a binary relation. Is a binary relation. This is always the case for any group action. I mean, check tilde is an equivalence relation. And now you can pass to the quotient set. So take the quotient set A mod tilde. Tilde is an equivalence relation. Just take its quotient by, just take the quotient of A by tilde, by which we mean just look at the set of all equivalence classes. In this case, the set of all orbits. Yeah, so I should also say check that equivalence classes are orbits of the action. So take A over tilde. This quotient set will be denoted by A over G, because the tilde relation is essentially induced by the action of the group G. So I'll write it as A over G. This is the set of orbits, and the claim is that this is exactly the co-limit of that functor. This set is exactly the co-limit of that functor. Now the co-limit of the functor is in particular a cocon on the functor, right? So it consists of it exactly is a pair C comma an arrow that is a function u from A to C. So we are claiming, so coming back to the problem, claim is this, that the co-limit of the functor f is, which is exactly what we want to find, is exactly, I mean the vertex of the universal cocon on the functor f is exactly the set A over G, and we should have a function from A to A over G, right? What function should we take, Shrutin? Is there a canonical function that we can think about from the set A to some quotient of it?
Yeah, just send an element small a to the equivalence class it belongs
So the
to.
canonical projection map, right? The quotient map. So this is our quotient map. So which sends, so we'll write it by, you denote it by pi. It sends every element little a to the orbit of A, the equivalence class of A. So yeah, OA or orb A. Oops. I will not try to put problems, domain specific problems from next time. I mean that's not the purpose of the course as well. The course, I mean groups etc. are only useful for examples. So I'll try to avoid keeping domain specific examples so that people from computer science and different areas can actually appreciate the subject. But yeah, trust me, this is the only problem that we have. So A gets mapped to orb A. That is how pi works. We claim that this will be the co-limit, and you can check that this is indeed the co-limit. So what do you need to verify? You need to verify that this cocon that we have, this is you can check that this is indeed a cocon, in the sense that, so what do you need to verify? You need to verify that for it to be a cocon, you need to verify that if composed with, I mean the function composed with any sigma g should be equal to the function itself. So pi composed with sigma g acting on any element A of A is pi of G dot A. The equivalence class of G dot A is exactly the equivalence class of A, because the equivalence relation identifies A with something that comes from A, G times A for some G, right? So A and G dot A are equivalent, which means their equivalence classes are exactly the same. So pi of pi composed sigma G of some element A is pi of G of A, which is orbit of A, right? And this is orbit of A, which is pi of A exactly, and this is, yeah, pi composed G of A. We don't need to write anything else. This is true for all G in G, A in A. In particular, it is true for all A in A, which implies that pi composed with sigma G, this function, this map is exactly equal to pi. So this we have, right? That means, so this pair A over G comma this quotient map pi from A to A over G is a cocon on the functor f. We just need to check that this cocon is the universal cocon on the functor f. So we have already verified the coconness part. We have verified that this A over G comma the quotient map from A to A over G is indeed a cocon. We just need to verify that this cocon is universal among all cocons. That exactly means that this will be the co-limit, right? So I have already explained what a cocon being universal means. It means exactly this. That is, it means that for every arbitrary cocone on the functor f, there should exist a unique function which makes this commute, right? So we just need to verify this part. Just take an arbitrary cocone, check that that factors uniquely to the universal one. I mean through this A over G. Now let x comma a to x f be a cocone on f. That is, what this means is x is a set, f is a function, and f composed with sigma g is equal to f for all g in G. That is what we saw. That is what a cocone means, right? We need to show that. So need to show this description of the universal property, right? Need to show that. So this is our description. Where did I write it? Yeah, need to show that there exists a unique function from your co-limit, your suspected co-limit, which in this case is a over g, to x, making this commute. So need a unique function from a over g to x, f prime, such that f prime, or I should write it like this. I mean, there should exist a unique function such that this commutes. I mean, there should exist a yeah. I mean, the factorization should be unique. There should exist a unique function such that this commutes. The what should I say? I mean, the uniqueness is subject to this. I mean, uniqueness is for this commutativity, right? In other words, if there is another function which makes this commute, the two functions should be equal. So I need a function from a over g to x, f prime, such that f prime is the unique function such that f prime composed with u is equal to f. So f prime composed with pi is equal to f. So how do you find, the question is how do you find this function? So a over g to x, you need to define some f prime function, and an element here is an orbit of the action. Where should you send it to? Everything is given here to you. In particular, you have a function f from a to x. So I could try sending it to f of a, but that of course raises the question of well-definedness of this f prime. Now f prime is well defined precisely because, why is f prime well defined? Precisely because this is a cocone on f. That is precisely because f composed with sigma g is f for all g in G. So note that if orbit of a is equal to orbit of a prime, by definition that means that a is related to a prime under that equivalence relation tilde, that is there exists some g in G with g dot a is equal to a prime. G dot a is just sigma g applied on a, right? And we know that f has this property that f composed with sigma g is f, which implies that f of sigma g of a is f of a, right? That is f of g dot a is f of a, that is f of g dot a is f of a prime, right? So f of a prime is f of a, which shows that f prime as a map is well defined. So it's a map. This assignment is well defined. So f prime is a map, right? F prime is, let's write it like this. So f prime is a map from a over g to x, and it certainly does make this commute. I mean, it certainly does say this. satisfy this. Also observe that by definition f prime of orb of A was defined to be f of A, and f prime of orb of A is exactly f of the quotient map applied on A. That is what the quotient map pi is doing, right? Sends any A to orb of A. This is true for all A in A, which implies that f composed with pi is f, which is exactly what f prime composed with pi is f, which is exactly what we wanted, right? And how do you show uniqueness? Again, if double prime from A over G to X is a function such that if double prime composed with pi is also f, what is the problem here? What is the point here? Then f double prime of pi of any A is f of A, which is f prime of pi of A for all A in A. But f double prime of pi of A is exactly f double prime of orb A, which is exactly f prime of orb A. And the elements of the domain of f prime or f double prime are exactly orb A's, where A varies in A. Each equivalence class is an element, right? So this is true for all A in A. So this is true for all orb A in A over G in the domain, which implies that f double prime is equal to f prime. So what we ultimately have is, we have this, that this firstly is a cocone on the diagram F, and secondly every arbitrary cocone on the diagram F factors uniquely through this cocone, which means that this cocone is exactly the universal cocone on the diagram F, right? That is what it means. So this cocone is a cocone on the functor F such that every arbitrary cocone on the functor F factors uniquely through this cocone in this sense, right? So this is exactly what it means to say that this cocone is a universal cocone on F, which exactly means that this cocone is the co-limit of F, right? So the co-limit of F is, I'm just repeating things here, but again the point is that the co-limit of any functor F is a universal cocone on the functor F, right? The co-limit of any functor F is a universal cocone on the functor F. That is, this is what it means, right? So yeah, that does finish the proof. So A over G together with the projection map pi from A to A over G is the co-limit of F. That's all. That finishes the problem. It was a bit lengthy, but yeah, we'll get to the next one. Let's take a 2-minute break just to clear our minds. The idea behind any such kind of problems in which you have to find the limit of a functor F or the co-limit of a functor F is to approach it in this way. So the definition of the limit of a functor F is that it is a universal cone on the functor F, right? So that has a specific meaning. Dually, the definition of the co-limit of a functor F is that it is a universal cocone on the functor F, which in this case exactly means what I have mentioned here, right? This is what this entire part exactly means. Exactly is the meaning of what it means for something to be a universal cocone, right? This is what it means for something to be a universal cocone. Okay, so the co-limit of F is just the universal cocone on the functor F. So the idea or the way to approach is you first find a cocone, try to guess a cocone which you think should be the co-limit. It's always a canonical one. Here the functor F was simple, we could guess it. In many cases it will be simple, you can guess it, and then just show that it has the universal property of a colimit. That is, this holds. Okay. Yeah, let's take a 1 minute break. And do you have any questions you want to ask? Is everyone stunned right now by the content of the last of this problem? It's pretty simple. Just, I mean, I understand that it's not exactly a category theoretic question, so to say. Yeah, you want to say something, Srisha?
Um, no, I just unmuted myself. If you were going to ask something.
Okay. I'm not asking you. I'm just asking, do you have any questions to ask right now?
No,
Okay.
not.
Yeah, let's get back to category theoretic questions again. Okay. Again, we get back to simple problems. So let's see be a category. F be a regular epimorphism in C. So yeah, I hope that you guys remember what the definition of a co-equalizer is. Do you or do you not? Otherwise, we have to get to that as well. What is the last problem? Okay. Let's see. We'll get to that, but solution. So again, the co-equalizer is a co-limit. So co-limit of a diagram of this shape. Okay, any diagram from any functor from this category into some category A exactly looks like this. Some object A, some object B together with an arrow F in A, an arrow G in A. Okay, so it's exactly some object A, some object B together with an arrow F from A to B and an arrow G from A to B. This is exactly what a diagram in A looks like of this shape. And the co-limit of this functor is exactly the co-equalizer. The co-limit of this functor is by definition the universal cocon on this functor, which you can check is exactly the co-equalizer of this parallel pair of maps. So what exactly is the co-equalizer? So given two maps A to B, F, G in some category A, given two arrows F, G in some category A, the co-equalizer is some object C of the category together with an arrow from B to C such that, so let's say this is C, such that CF is equal to CG, and secondly, so which exactly should corresponds to the fact that you have this should give you a cocon on your diagram, and for that cocon to be the co-limit you only require that that cocon should be the universal cocon on the diagram. That is what the co-limit is by definition exactly. So we want this cocon to be the universal cocon, by which we mean that this C, which has this property that CF is equal to CG, should be the universal one among all arrows with the same property. So secondly, if you have, so let's write it as a picture, so such that CF is equal to CG, and the universal property is that if you have an arbitrary arrow B to X, right, let's say H, such that, so for all H such that HF is equal to HG, that H should factor uniquely through C, by which we mean that there should exist a unique arrow let's say h prime from C to x, making this triangle commute. Okay, this is what it exactly means for the pair little c comma capital C to be the co-equalizer. So given two arrows fg in a category from an object A to an object B, the co-equalizer of this parallel pair is some object C of the category together with an arrow little c from B to C, such that first of all CF is equal to CG, and secondly for any arbitrary object x and any arrow h from B to x such that HF is equal to HG, there exists a unique arrow h prime from C to x, making this triangle commute, that is h prime C should be equal to h. Okay, so that is the idea of a co-equalizer, or that in fact that is the idea of a co-limit in general. So you have some diagram, the co-limit is the cocone which is closest to the diagram, okay, in the sense that the co-limit object is connected to the diagram by the smallest possible arrows. In this case the smallest possible arrow is C, because any arbitrary arrow which has this property factors through C. So in other words, h can be written as a, so h has a unique factorization in this way. H is h prime C. Any h is h prime C. So in that sense you can think of h to be a longer arrow than C. Think of these arrows as natural numbers. So h is just the product of two arrows, that's all. So h is certainly bigger than C. So every arbitrary arrow should be bigger than C. In other words, the universal arrow should be the smallest arrow coming out of B. Okay, so by smallest I therefore mean that it should be the object, so the object C should be the closest to the object B. Okay, the object C should best approximate this pair FG. That is what a universal arrow means, or a universal construction means. Find the best possible approximation of your given data. Find the smallest possible arrow related to the given data. Okay, that is what exactly the universal a universal construction exactly is. The smallest possible arrow related to the given data. That is the idea of the co-limit. That dually that is the idea of the limit as well, right? The limit is the smallest possible arrow which the limit is the smallest possible arrow which goes into your data. In this situation, if you took this pair A to B FG, the limit would be an object E together with an arrow E together with an arrow from E to A. So it is an arrow which goes into the data, which is universal, that is which is the smallest possible arrow going into A with this property that F composed with this arrow is G composed with this arrow. So it's the smallest one, means that if you take an arbitrary object X together with some arrow X to A, that arrow should factor uniquely through this smallest possible arrow, through this universal arrow. So there should exist a unique map from X to E making this commute. So that this arbitrary arrow is actually composition of this with this. Okay. So E is the object that is closest to your data, in the sense that E is equipped with an arrow going into the data starting at E, right? So the limit or the equalizer in this particular case is the smallest possible object, I mean the smallest possible arrow going into your data. Okay, in general the limit of a diagram is the smallest possible cone on the diagram, the shallowest cone on the diagram, the cone with the smallest possible height. If this is your diagram, the limit is some object together with arrows, that is some cone on the diagram which is closest to the diagram, which best approximates the diagram. So anything else, any other cone on the diagram should factor uniquely through this limit cone. Okay, should be larger or more, have a greater height, so to say, than this cone. That is what something being universal means. In particular, that is what being a limit means. It is a universal cone on a diagram, exactly. And dually, the co-limit is exactly the universal co-cone on a diagram. Exactly. Okay. So yeah. Uh, yeah, this is the definition of the co-equalizer. So given a parallel pair Fg, the co-equalizer of this parallel pair is an object C together with an arrow little c from B to C, such that first of all Cf should be Cg, and for every object X together with an arrow H from B to X, such that Hf is Hg, you should have some unique arrow H prime from C to X, such that H prime composed with C is exactly H. Okay. What is we know what an epimorphism is. What is a regular epimorphism? This was taught this week. A regular epimorphism is exactly an arrow in a category which is an epimorphism and which is in fact the co-equalizer of some parallel pair. So co-equalizers are always epimorphisms. This you can prove using using the definition of a co-equalizer. So if C is a co-equalizer of some parallel pair, it will always be an epimorphism. And what is a regular epimorphism? Exactly those epimorphisms are regular epimorphisms which are co-equalizers. That's the definition of a regular epimorphism. So when I say that F from A to B is a regular epimorphism in C, I mean that there is some parallel pair whose co-equalizer is F. Okay, so let's write it nicely. I hope that you remember the definition of co-equalizer. So by definition, there exists some parallel pair let's say C to A. What notations can we use? LR, let's say, of arrows in your category such that, oh, script C, yeah, thank God, such that this is a co-equalizer diagram. LR A to B F, yeah, let's A to B F is the co-equalizer of L comma R, L and R. So this is the data given to you already, and moreover what it says is that the following square is actually a pullback square. So by this I mean X is, of course you understand, is an arbitrary object. You are taking the arrow F, and you are computing the pullback of this cospan, which is some object X together with arrows. So what the intention of this statement exactly is that the pullback of this cospan of this diagram exists. That's all that we want to say here. Okay, so the pullback of this diagram in the category exists. Let's call the pullback X together with the projection maps pi 1 and pi 2, together with the maps pi 1 and pi 2, the structure maps of the pullback. So this is given to you that the pullback of F along itself exists. By the way, if you take any arrow in a category, and if the pullback of that arrow along itself exists, then that pair of arrows that you get as part of the pullback, in this case pi 1 and pi 2, are called the kernel pair of the arrow F. And the name comes from the fact that this actually captures kernels of homomorphisms. Okay, so more on that, not just more on that later. The point is that this pullback exists. The pullback of F along itself exists. What you need to show is that F is actually the co-equalizer of this parallel pair. So from X to A you have the map pi 1, from X to A you also have the map pi 2, right? So X to A you have pi 1, X to A you have pi 2. We need to show that F is actually the co-equalizer of this parallel pair. Very easy problem. How do you show this? What we know, or what we are given, is first of all F is the co-equalizer of some parallel pair LR, which we have considered in this case, and moreover the pullback of F along itself exists, which is given by this square, commutative square, which is a pullback. So so we want to show that what do we want to show? We want to show that if you take x to a, pi 1, pi 2, we want to show that this same f is the co-equalizer of pi 1 comma pi 2. We know that f is a co-equalizer of some pair of arrows LR. We want to show f is actually the co-equalizer of pi 1, pi 2. So how do you show this? So we'll write everything in diagrams now. So let's keep this pullback square in mind. Let's record it once again. A to B, F, right? X pi 1 or pi 2, let's say pi 1. This is a pullback square given to you already. We also have C to A, LR A. The co-equalizer of this parallel pair is F. This is given to us. We want to show that the co-equalizer of pi 1, pi 2 is also F. So first of all, if you want to show that the co-equalizer of pi 1, pi 2 is also F, first of all, what do we need to show? We need to show that F composed with pi 1 is F composed with pi 2. Is that already given to you? Someone quickly say it. Someone quickly say why is F composed with pi 1 equal to F composed with pi 2? Why is it the case? Yeah. Why is
Is
this?
it because of epimorphisms on L and R?
No. Why is F composed with pi 1 equal to F composed with pi 2? What is this square given to you? What square is this?
The square is a pullback.
So in particular, this square is a. In particular, this.
Epimorphic.
No, that.
It's
no.
a commutative.
It's a commutative square. This is given to you. It's a pullback, so it's a commutative square. That's all. Since this square commutes, that means that pi 2 if you take this, commutative means that if you take this arrow and this arrow, compose them, this should be equal to this arrow composed with this arrow, right? Any two sequences of arrows in the diagram with the same starting object and with the same ending object will yield by composition equal arrows from the starting object to the ending object. So F compose pi 2 is F compose pi 1. Since the above square is a pullback and hence commutative. Right, so we already have this. I want to show that F is the universal such arrow such that F pi 1 is F pi 2. That is, this exactly means that if you take an arbitrary arrow from A to X, so you not X, we need to take some other object. I hope I didn't use X elsewhere. Yeah, thank God. So X to A, pi 1, pi 2, F is given B. So take an arbitrary arrow from A to some object Y, let's say your arbitrary arrow is, did we use H anywhere? No. H. Suppose h is an arbitrary arrow such that h composed with pi 1 is h composed with pi 2. H composed pi 1 is h composed with pi 2. So for all, so h is an arbitrary arrow such that h composed pi 1 is h composed pi 2. What you need to show is there should exist a unique arrow from B to Y making this commute. That is what universality here means. So that is what being a co-limit means exactly. So this will conclude that if this would show that f is the co-equalizer of this parallel pair pi 1 pi 2. So just take an arbitrary arrow h from a to y, show that it factors through f uniquely. So how do you get this? Keep in mind f was already known to be a co-equalizer but of some other parallel pair, namely LR. We need to use that fact. So we have an arrow from a to y making such that h pi 1 is h pi 2. We can of course to get a unique arrow from b to y, we can of course look at this co-equalizer, right, and try to take this arrow from the same arrow from a to y, right, and work with it. So we'll do this exactly. So how should I write this? Let h from a to y be an arbitrary arrow in your category C such that h composed with pi 1 is h composed with pi 2. We need to show that there exists a unique arrow from B to Y making this triangle commute. So since C to A LR F is a co-equalizer, we need to use this fact. So we can take the same arrow h from a to y. We just need to show that HL is HR. To use the unit to obtain an arrow from B to Y, we need to show that HL is HR. We just know that h pi 1 is h pi 2. How do you do this? How do you show that HL is HR exactly? Just look at the pullback. Yeah.
Do we again use the property of that square?
We have to use the property of that square to get to the fact that HL is HR. So how do you show? So H is an arrow such that h pi 1 is h pi 2, right? So let's try to use that. Wait a second, is something wrong? H is an arrow such that h pi 1 is h pi 2. Okay, yeah. So just look at this square. I think we can use h a bit later. Let's come to h a bit later. uh, I mean, that is, we need to consider h at the end, but let's keep this in the background for some time. I mean, using just these two pieces of data, we can extract some more information that we would like to use, which we haven't yet, and that will actually solve the problem easily. So let's cut it for some time. We'll bring it back. So you have these two pieces of data. This is a pullback square. This is a co-equalizer diagram. We just have this, that f compose pi 1 is f compose pi 2. Let's look at this pullback square more closely. X to a pi 2, x to a pi 1, a to b you have f, a to b you have f. This is a pullback square. Now take the object C. From C to A you also have an arrow L, right? This is what I'm referring. C to A you have L, C to A you also have R, right? And F is the co-equalizer of this parallel pair. Exact in particular means that FL is FR, right? So this means that this composition is this composition. That is this big square commutes using this arrow, this arrow, this arrow, and this arrow. This big square commutes. What does that mean? By the universal property of pullbacks, you should get a unique arrow from C to X, making this commute as well as this commute, right? Let's call this unique arrow to be N, let's say. So by universal property of the...
So if we have R and L, we also have N because of the property of the...
Yes, exactly. That is what we have extracted so far. So by universal property of the pullback, there exists a unique arrow N from C to X such that pi 2 N is equal to L and pi 1 N is equal to R. This is what we have. And now you see this diagrams, this two parallel pairs pi 1, pi 2 and LR can be connected, okay, using our N. Okay, how exactly? So what you do is, you have this, you already have this, x to a pi 1 pi 2, and from C to X you take N. Now pi 2 N is exactly L, right? Yeah. So this is L exactly, and this is R exactly. Okay, and now we bring in our arbitrary data and show that it factors uniquely through F. So let H from A to Y be an arbitrary arrow. So first of all, we know that this F from A to B, yeah, what do we want to show? We want to show that F is a co-equalizer of this parallel pair of arrows, right? Pi 1, pi 2. So first of all, F pi 1 is F pi 2, which we already have because the square is a pullback and hence in particular commutative. Now assume that you have an arbitrary arrow H from A to Y such that H pi 1 is equal to H pi 2. That is what we have assumed. Let H from A to Y be an arbitrary arrow in C such that H compose pi 1 is H compose pi 2. What I want is a unique arrow from B to Y such that makes this triangle commute, right? But I don't know if it's a co-equalizer. I have only proved that F compose pi 1 is F compose pi 2. But I know that F is a co-equalizer of this parallel pair, right? So I just use this arrow N to bring L and R into the picture. That is what we want, right? So H composed pi 1 composed N is H composed pi 2 composed N, because H composed pi 1 is H composed pi 2. So C to C to N, I mean C to X to A pi 1 pi 2 A H Y. This upper composition is yeah, pi 2 n is L, pi 1 n is R. So yeah, which implies H composed with R is H composed with L, right? So pi 2 composed n is L, I hope so. So this is L, this is R, right? So H is such an arrow such that H composed R is H composed L, right? If we already knew was the co-equalizer of L and R from A to B was the co-equalizer of L and R, since F is the co-equalizer of L and R by the universal property of co-equalizers, this arbitrary arrow H should factor through F, right? This is F. Yeah, there exists a unique arrow from B to Y, let's say F prime, such that in your category such that there exists unique F prime such that F prime composed with F is equal to H. F prime is a unique arrow making this triangle commute, right? So F prime composed F is H, right? And now you have an F prime from B to Y, right? That is what we wanted. What did we want initially? We wanted to show that F is a co-equalizer of pi 1 and pi 2, by which we mean that every arbitrary arrow H, which such that H composed pi 1 is H composed pi 2, should factor uniquely through F, right? So we wanted a unique arrow from B to Y, which makes this commute, just this small triangle commute. We just used our arrow N to translate this problem to L and R, right? And we know F is given to be the co-equalizer of L and R. H is an arbitrary arrow such that H composed R is H composed L. We have proved this because we assumed H composed pi 1 is H composed pi 2. We proved from this that H composed L is H composed R. F is a co-equalizer of L and R. So there is a unique arrow of F prime from B to Y such that F prime composed F is H. And that is what we wanted in the first place. There should exist a unique arrow.
Okay. How did we get F dash again? We derived F dash, right?
We didn't have F dash, but so what did we take? We had X. We had two arrows. We had X. We had two arrows. X to A, pi 1, pi 2. We took an arrow A to H, A to Y H, right? Yeah, let's call it H dash, not F dash. There exists unique H dash. H dash composed F. I'll come to what you are asking, but yeah, H dash. Let's call it H dash. H dash composed F is H. Yeah. So the point is we had X, A. We had two arrows X to A, pi 1, pi 2. We know that, I mean, we don't know anything yet. We want to show that F is a co-equalizer of pi 1, pi 2. We have proved that F composed pi 1 is F composed pi 2. We assume that there is an arbitrary arrow H from A to Y such that H composed pi 1 is H composed pi 2. I want a unique arrow H dash from B to Y, right?
Yes.
So what we did is we take C. We have an arrow N, right? We already obtained this arrow N, and we know that N is that arrow such that pi 1 composed N is R, pi 2 composed N is L, right?
Oh, this is from the square that we.
Yes, we had that. We had that N is the unique arrow such that pi 1 composed N is R and pi 2 composed N is L. Such an arrow, of course, exists using the universal property exactly, and uniqueness is also from the universal property exactly. So you have this N, and you can translate the problem or bring L and R into the picture. Now H composed with pi 1 is equal to H composed with pi 2. we have used this to show that H composed with R is also H composed with L. So what we now have is this, right? So we have C to X, I believe. Sorry.
Yes. C to C. N
C-
arrow X is what,
C to,
what
yeah.
you do.
So C to A ultimately. This is C to A R, C to A L, and A to Y H, and A to B F. We know that F is the co-equalizer of L and R. That we had, right, from the beginning.
Yes.
So that means you have a unique arrow from B to Y, H prime, which makes this triangle commute. And that is what we wanted, right?
Oh, okay. And it's from B to Y because using F we derived H.
No, H is arbitrary. Yeah, okay, you can say it in that way. Yeah. I mean, H factors uniquely through F. So there exists a unique arrow from B to Y.
Ah, okay, got it.
And this is exactly what we wanted. So F is the co-equalizer of pi 1 and pi 2. Yeah, I'll end here. Every week I continue for I don't know why we cross 8, but I'll leave this problem as an exercise. Just replace group by set here. I mean, it doesn't really make a difference. It's exactly the same, but have a look at this one. You can use, I mean, the universal property. You don't actually need to. So what I'm asking is I'm giving you a diagram D of shape I in the category of sets.
Okay.
And what I'm asking you is so the category of sets is one of those nice categories which has this property that limits of every diagram exists in set. So set has all small limits. Every diagram in set has a limit. The limit exists. So set is a complete category. So this diagram will have a limit. I just want you to find an explicit description of the limit. Now, of course, you can make an educated guess, obtain a cone on your diagram, then show that this cone is actually the limit cone. That is, this cone is exactly the universal cone on this diagram. You can take that approach, make an educated guess, or you can use some nice trick, which is exactly why I have given you this problem. You don't need to guess anything actually here.
Okay, explicit description means like a rigorous proof.
No, explicit. So this is a diagram in the category of sets, right? So the limit of this diagram will be an object in set. So it will be a set, right?
Okay.
So now set, I mean, a mathematical object which is, I mean, the mathematical object. How should I say? I mean, a set is a mathematical object and it has this nice property that it has elements in it, right?
Yes.
Internal data. It has internal data. So what I want you is to find the elements of that set. That is what. Give an internal description of the limit of D. Give an internal description of that set. What exactly is the set? Okay.
Okay.
Yeah.
Understood.
Yeah. So that's all for this week.
Thank you, sir.
Yeah. See you.
Sure.